Wow, welcome to Chapter 9, Nuclear Chemistry. We'll also be talking about the basic makeup of the nucleus, some facts about radioactivity, and some particles that are involved with radioactivity. And the really cool stuff about nuclear chemistry, it's unlike anything we've seen yet in chemistry. It's totally different in many ways, and we're going to find out why. So, natural radioactivity, there is radioactive species all over the planet, sometimes even in pitch clay. They can find uranium or radioactive particles that uh, stimulate a Geiger counter that picks up these particles flying through the air. Some of this can be dangerous, some of it not so harmful. It can, of course, in its worst case scenario, it can rip through our DNA and rip it apart. It can hurt our proteins. It can do damage to our body. And there are ways to protect ourselves from radioactivity. Um, there used to be a big market for potassium iodine back in the Cold War, as I understand. Potassium iodine was used to reduce radioactivity effects as best as possible, but there's some controversy about whether that works or is it dangerous. Of course, never take my word on medicine. I am not an MD or a doctor. I am a PhD doctor. So anyhow, radioactivity is a process by which atoms emit energetic particles or rays, and they do that in different ways. The radiation of the particles or rays emitted from the nucleus, we can use nuclear symbols to describe the nucleus or the nucleons. And in the nucleus, we have the neutrons, which have no charge, and we have the protons, which are positively charged. And these two nucleons are made up of all sorts of unique things like that our physicists are very interested in, but I won't go into detail. So it's not as simple as calling them as a proton and a neutron in the world of physics, but it's good enough for us chemists. Atomic symbol equals Z, which will be the number of protons, right? So the number of protons equals Z. So how are the elements arranged? By the number of protons, not their mass, but by the number of protons they have in their nucleus. Okay, so Z equals protons. The mass number, which equals A, that is the protons plus the neutrons. We know that the protons typically always equal the electrons, or they're at least close. If we have a cation or an anion, it may be one more electron or one less electron to the protons. But do not forget, Z is the critical feature to tell us how many protons an atom has, what kind of element it is. If the proton number changes, the entire element changes, right? So if we were to have a nuclear symbol here, we could have boron, which is anything but boring. There's tons of unique chemistry for boron. Boron has 5 protons. That will not change. That is the Z number. 5 equals Z, or Z equals 5. But it has a mass of 11. So the neutrons and the protons equal 11. So there are 6 neutrons and 5 protons, which weigh about the same, making boron as atomic mass number 11. And we also know that boron must have 5 electrons to balance the 5 protons. Okay, so boron, that's the element symbol, B for boron. 11 is the mass number, the number of protons, and the number of neutrons in the atom added together. 5 is the atomic number, the number of protons in the atom. 11 minus 5 equals 6. That's how many neutrons we have. This is just one particular isotope of boron. If we were to have another isotope of boron, we know that the Z number cannot change. The number of protons cannot change, but we can get more neutrons, so we could have boron 10 or we could have boron 12, and we would still have boron, but it'd be a different isotope. And in nuclear chemistry, we often call these nuclei. This is, of course, not the only isotope. We do have boron 10. It has 1 less neutron. And how many protons and neutrons does boron 10 have? Of course, it has to have 5 protons. And now instead of 6 neutrons, it has 5 neutrons. So we also can do this with carbon. Carbon is very important because we are a carbon-based species. and carbon has, as we know it, to be carbon, it must have 6 protons. So in every form of carbon here, every isotope or nuclei, we have 6, 6, and 6. That never changes. Can't change, or we would not have carbon. Okay, we'd have some other element. And we don't do that in regular chemistry, right? We don't change carbon into nitrogen. We don't do that. But we're getting into nuclear chemistry, so be wary. We can do things that we never could do before in any of our chemical equations, which uh, will have these nuclear equations. So each nucleus contains the same number of protons, only the neutrons will differ. So with different number of neutrons, the mass of the isotope is different. So the mass of carbon 12, of course, is 12. It has 6 neutrons and 6 protons. Carbon 13 has 7 neutrons and 6 protons. Carbon 14 has 8 neutrons and 6 protons. And we see these models of the nucleus, what they call the protons and the neutrons can be generically called nucleons. Unstable isotopes. Some isotopes are stable, and therefore the radioactivity doesn't register. They're not emitting particles. They are completely stable, as things like some of the potassium and sodium. We don't have to worry about those being radioactive. But we do have radioactivity, and that can be measured in a multitude of ways. It can be measured by alpha particles coming off, beta particles coming off, positrons coming off, gamma rays being emitted. So the symbol for these we write nuclear equations, no longer just a chemical equation. It is now a nuclear equation because the nucleus is being changed. We need to be able to write the symbols for the isotopes, and we'll see that with alpha, beta, positron, and gamma rays. So alpha particles represent, really it's a helium species, typically missing its electrons. But an alpha particle has 2 protons and 2 neutrons. It's the same as a helium nucleus, which is He2 plus. It is slow moving and stopped by small barriers, relatively slow moving, very fast comparing it to us humans, symbolized in the following way: 4/2 He2 plus. That is the mass, which is 4, the number of protons, or the Z value, which is 2, and therefore we have 4 and 2. We can get rid of the 2 plus. They do that a lot of times because we just know that when we're dealing with nuclear chemistry, or we can just call it alpha, or an alpha particle, and sometimes this is 4/2 as well. Beta particles are faster moving than alpha particles. Makes sense. They're much smaller. Emitted from the nucleus as a neutron is converted to a proton. So the neutron loses this negative particle that turns it into a positively charged species as a proton. And so these higher speed particles are more penetrating than alpha particles. The Z goes up, meaning because we add protons when this happens, we lose the negative charge on a neutron. The neutron gets converted to a proton. So the number of protons go up and the number of neutrons goes down by 1. The number of protons goes up by 1. The weight stays the same in some reactions. And so we can write a beta particle, or a beta particle emission, as 0 minus 1 in E for electron, or 0 minus 1 for beta, or just simply beta for beta particle. Positron has the same mass as an electron or a beta particle as well, same mass, but it has the opposite charge of an electron. It is actually a positive charge coming off, and it comes from the nucleus. This comes from the proton. The proton loses its positive charge, and the proton gets converted into a neutron. So it's the very opposite of a beta particle. The Z value then goes down by 1. So you're going to lose a proton and gain a neutron. And of course, when the Z value changes, you change the elements. So look at what we're doing. This is totally different than anything we've seen before. We can have nitrogen, and nitrogen can lose a proton and become carbon. Or we can have carbon and it can add a proton and become nitrogen. So this is totally different than anything we've ever seen. It's even different than, it's kind of outside of all the rules that we've learned. Gamma ray, again, has no mass. We know that light has no mass, that we can, light does it, light can, and electrons can interact, but light is not necessarily electrons. It's not electrons at all. But we know that electrons do interact with light energy. Gamma rays, as well as light, have really no particle size to mention of, but it's very powerful and pure energy, and it's highly energetic, and it can do damage to our DNA and our proteins as well. We don't want to get doses of gamma rays. And in fact, the Incredible Hulk showed the Hawk and the Hulk as he was being created into this monstrosity, this green super muscular mass of superhero, was hit with the gamma rays. And luckily, those mutations, in reality, we would think those mutations would be horrific. But in a comic book, anything can happen. But gamma rays are not something that life forms like us humans or any of our friends, our mammalian friends, would want to get exposed to. This has been Chapter 9. This is Chemistry 1001, Introductory Chemistry at ULM. You guys have a great day. I'll see you back here again with more from Chapter 9.